And we now look at double integration over more general regions. So consider the region D shown here. Now, it is clear that this region is bounded on the plane, so we can create some rectangle, call it region R, on the same plane that completely encloses D. In other words, D is a subset of R. Now suppose that z equals f of xy is defined on a general planar bounded region D. To develop double integrals over this region, we must extend the definition of the function to include all the points on R, and then use the concepts and tools from the previous video. So we define a new function, f tilde, on R as follows. F tilde f of xy will be f of xy whenever xy is in D, and it will be 0 whenever xy lies outside of D. In other words, f tilde will be f of xy everywhere in here, right? But anywhere else in the rectangular region, f tilde will be 0. Now, we could technically have some difficulties if the boundary of D is complicated. So we will assume that the boundary is continuous, simple, piecewise smooth, closed. If f of xy is continuous on a closed domain D whose boundary is a simple, closed, piecewise smooth curve, and if R is a rectangular region that encloses D, then the double integral over R of f tilde of xy exists. From this, we can see that the double integral of f of xy over the region D is equal to the double integral of f tilde of xy over the region R. So this introduces some new concepts: vertically simple versus horizontally simple regions. So we say that a region D in the xy plane is vertically simple or of type 1 if it can be expressed as a set of all ordered pairs xy such that A is less than or equal to x, less than or equal to b, and g sub 1 of x is less than or equal to y, less than or equal to g sub 2 of x. A region D in the xy plane is said to be horizontally simple, or of type 2, if the region D can be expressed as the set of all ordered pairs xy, such that c is less than or equal to y, less than or equal to d, and h sub 1 of y is less than or equal to x, which is less than or equal to h sub 2 of y. So this slide shows some vertically simple regions. Right, we have this region here. X is between values a and b, and then we say that y is bounded by two functions of x, so two curves. Here we have another one, and again, x is bounded between a and b, and y is bounded between two curves written as functions of x, and same thing over here. This slide shows horizontally simple regions. Here we see that y is bounded between c and d, and then x is bounded between two curves written as functions of y, and then the same thing here. So we now begin to look at how we can integrate over this general region. So we assume that we have a vertically simple region D. A similar argument can be used for a horizontally simple region. What we do is we choose a rectangle R that encloses D, and let f tilde be the function that was defined earlier. Now, it can be shown that Fubini's theorem holds for functions that are defined over some domain R in R that is 0 outside of this domain. So we can apply Fubini's theorem to f tilde. That is, the double integral over the region D of f of xy is equal to the double integral over the region R of f tilde, which is a integrated integral, the integral from a to b, of the integral from c to d of f tilde. However, since f tilde is zero outside of this region D for a fixed x, f tilde is zero unless y satisfies this inequality. So, what we can actually do is we can write this inner integral here as the integral from g1 of x to g2 of x of f of xy dy. Substituting this in for here, we get our next theorem, which is the strong form of Fubini's theorem. So if D is a vertically simple region, then the double integral over D of f of xy dA is the integral from a to b of the integral from g1 of x to g2 of x of f of xy dy dx. Now again, the argument that we used before was for a vertically simple region, but a similar argument holds for horizontally simple. So if D is a horizontally simple region, then the double integral over D of f is the integral from c to d, the integral from h1 of y to h2 of y, f of xy, dx, dy. So let's go ahead and evaluate the double integral of x squared times e to the xy over a region D, where D is this. Okay. So the double integral over D of x squared e to the xy dx. So we're integrating with respect to y first, x last, so the outer integral will be from 0 to 2. Then the inner integral will be from x over 2 to 1. Then we have x squared e to the xy dy dx. So this will become the integral from 0 to 2 of x squared times 1 over x e to the xy, evaluated y equals x over 2 to 1. So that just simply now becomes, the integral from 0 to 2 of x, then times e to the x minus e to the x squared over 2 dx. So if we now distribute that x through, we get the integral from 0 to 2 of x e to the x minus x e to the x squared over 2 dx. Now using an integral formula, x e to the x is x minus 1 times e to the x. And then we can evaluate the second integral by simple u substitution and get minus e to the x squared over 2. Write that. And then this whole thing is evaluated from x equals 0 to 2. So what we get is we get e squared minus e squared plus 1 plus 1. I'm sorry, and that is 2. So this double integral evaluates out to 2. If we now look at this double integral, all right, so integrate 3x squared plus y squared over this region here. So this is now horizontally simple. So double integral over d of 3x squared plus y squared will be the integral from negative 2 to 3, integral from y squared minus 3 to y plus 3 of 3x squared plus y squared. dx dy. Alright, so this will equal the integral from minus 2 to 3 of x cubed plus xy squared evaluated from y squared minus 3 to y plus 3. So we have the integral from minus 2 to 3 of y plus 3 cubed plus y plus 3 times y squared, then minus y squared minus 3 cubed minus y squared minus 3 times y squared. So after doing some algebra, this will simplify to the integral from minus 2 to 3, negative y to the 6th, plus 8y to the 4th, plus 2y cubed, minus 12y squared, plus 27y, plus 54. So this will evaluate to negative y to the 7th over 7, plus 8y to the 5th over 5, plus y to the 4th over 2, minus 4y cubed, plus 27y squared over 2, plus 54y. And then that will be evaluated from y is equal to negative 2 to 3. And that will evaluate out to 2,375. Now we wish to evaluate 2x plus 5y over the region shown here. So if we actually look carefully at this, we can split this region into 3 separate regions. We'll have this region here, we'll have this region here, and we'll have this region down here. Now, if we look at this, let's call this region down here as D1. We'll call this region here as D2, and this region as D3. Well, then, our double integral over D, notice is now D is a union of 3 regions that do not intersect. So we can write this as the integral over D1 plus the integral over D2 plus the integral over D3. The only job now is to express each of these 3 regions as either horizontally simple or vertically simple. So if we look at D1, let's express this as a vertically simple region. So we're going to kind of go like this. Well, x will go from -2 to 0, right? I'm sorry, this is horizontally simple, not vertically simple. So y is going to go from -4 to 0, and x will go from -2 to this curve right here, which is y minus y cubed over 16. d2, let's now say, is vertically simple, right? So x will go from -2 to 0, and y will go from 0 to this curve here, which is x plus 2 squared. And 3 can be expressed as horizontally simple. So y will go from 0 to 4, and x we can see will range from 0 to, again, this curve. We will now evaluate each integral individually, and at the end we can add them all together. So to start, we look at the double integral over the region d1 of 2x plus 5y. So this will be the integral from -4 to 0, integral from -2 to y minus y cubed over 16. Then we have dx dy. So we'll have the integral from -4 to 0 of x squared plus 5xy evaluated -2 to y minus y cubed over 16. So after some algebra, this will become the integral from -4 to 0, y to the 6th over 256 minus 7y to the 4th over 16 plus 6y squared plus 10y minus 4. And this will evaluate to, this is a Calc 1 integral, so I'll let you verify this, to 1696 over 35. Right, so this is the integral for d1. If we now look at the integral for d2, this will be the integral from -2 to 0 of the integral from 0 to x plus 2 squared. So this will give us the integral from -2 to 0. I'm sorry, this is not dA, this is dy dx. So we'll have 2xy plus 5y squared over 2 evaluated y is equal to 0, x plus 2 squared. This will give the integral from -2 to 0, 2x minus x plus 2 squared plus 5 times x plus 2 to the 4th all over 2 which will evaluate out to 40/3. Now what's left is the double integral over d3. So this is going to be the integral from 0 to 4 of the integral 0 to y minus y cubed over 16 dx dy. This will give the integral from 0 to 4 of x squared plus 5xy from y equals x equals 0 to y minus y cubed over 16 which will give us the integral from 0 to 4 y minus y cubed over 16 squared plus 5y times y minus y cubed over 16, and that'll evaluate out to 1664 over 35. So our total integral is going to be the sum of those three integrals. So it'll be negative 1696 over 35 plus 40 over 3 plus 1664 over 35. This will give us 1304 over 105. Alright, so let's look at this integral by reversing the order of integration. So the first thing to do here is let's actually sketch the region that we're integrating. So we're going to go from 0 to root 2 for x. So 0, let's say this here is the square root of 2. And then from 0 to y equals 2 minus x squared. So 2 minus x squared is going to look something like this. Well, that is 2. So this would be our region in here. Now, we want to go from dy dx to dx dy. So we now want a horizontally simple region. Let me actually write this out as y equals 2 minus x squared. Well, if y is 2 minus x squared, then x would be the square root of y minus 2. I'm sorry, 2 minus y. Right? We only need the positive because we're only concerned with positive y values. So this integral is now this integral. The integral from 0 to 2 of the integral from 0 to the square root of 2 minus y x e to the x squared dx dy. So we get the integral from 0 to 2 of 1/2 e to the x squared, evaluated 0 to root 2 minus y. So this will be the integral from 0 to 2 of 1/2 e to the 2 minus y, and then minus 1. This equals after some work, e squared minus 3 all over 2. We now look at some applications. So remember, a double integral is a volume. So we wish to find the volume of the solid that is bounded by the planes x equals 0, y equals 0, z equals 0, and 2x plus 3y plus z is equal to 6. Well, with z is equal to 0, let's just look at the xy plane. So we want 2x plus 3y equals 6, that line. So that would be this line here. And so this would be our region right in here. So this is 2x plus 3y equals 6. Now we can define this either vertically or horizontally simple. So let's make it vertically. So y is equal to 2 minus 2/3 x. So volume is the double integral over this region D of 6 minus 2x minus 3y dA, which is the integral from the 3 integral 0 2 minus 2/3 x of 6 minus 2x minus 3y dy dx. So this is the integral from 0 to 3, 6 minus 2x times y minus 3/2 y squared, y 0 to 2 minus 2/3 x. Right, so the reason for this is we can just represent 6 minus 2x as a function of x. It's a constant, right, with respect to y. So if we plug values in, we'll get the integral from 0 to 3, 6 minus 2x times 2 minus 2/3 x minus 3/2 times 2 minus 2/3 x squared. And that will evaluate out to 6. So some other applications. We represented double integrals as volumes. However, we can also represent areas of double integral. So the area of a bounded region D in the plane is given by the double integral over D of just dA. And finally, just as in Calc 1, or Calc 2 rather, we could represent the average value of a function over an interval as a single integral, we can represent the average value of a two-variate function over a domain as a double integral. And it's specifically going to be f bar of d is 1 over the area of the domain times the double integral of f of xy over that domain. Right, but this, of course, we just saw was the double integral over the domain of just dA, so it can be represented this way as well. And this is referred to as the average value or the mean value of f of xy over the entire domain. So we're not quite done with double integrals yet. In the next video, we will look at converting double integrals into polar coordinates.